Hello folks and welcome back to Fermi Physics Solutions. This next video is looking at the origin of the universe, in which it's a video series which I just call Where Did It All Come From. So what I want you to do is I want to start this off with a nice simple kind of imaginary experiment. And what I want you to do is I want you to imagine that I took a balloon and I filled it with two chemicals that when they react together produce a gas. And as you let time go on, that gas is going to start filling up the balloon and keep on filling up the balloon. And then what I do is I take a photo of the balloon as it fills up with gas. And so what I get is a set of photos that look like this. So after 20 seconds, my balloon was partially inflated. 30 seconds was a little bit more. 40 seconds a little bit more. And 50 seconds a little bit more again. Now, unfortunately, I just didn't get a chance to take photos for the first 20 seconds. But what I'd ask is, what do you think that the balloon looked like within the first 20 seconds in which I had the two chemicals reacting? So, as you can see, as the question would be like, what did the balloon look like after 10 seconds? So you kind of look at that and ask yourself, well, if the balloon is getting bigger every 10 seconds, then it's probably reasonable to take a position that the balloon was smaller. And I'll show you what that probably looked like. It looked there, it was actually smaller. So again, then I say, well, what did it look like at 5 seconds? So again, you look at the pattern and you see 10, 20, 30, 40, 50. The whole thing looks like it's getting bigger as time goes on. So it's probably reasonable to assume that it was smaller beforehand. And then you turn around and you say, well, at 5 seconds, 10, 20, 30, 40, 50, what did that balloon look like just at 1 second after the chemical reaction started and the gas was produced? And what we can see is it's just a very, very, very small balloon. Now, this is the ideal imaginary balloon. It doesn't go slack the way a normal balloon was. It just gets smaller and smaller and smaller. So what we can see here from the pattern very simply is that as time moves on, the balloon inflates and gets bigger, which means that if we were to go back in time, we could see that it gets smaller until it gets so small it's essentially in a single point. Another way I can look at this then is if I had a second balloon and I try to set it up, and this is what the balloon looked like for 20 seconds, 30 seconds, 40 seconds, and 50 seconds. And what I'd say is, well, based on the pattern that you see here, what is the most reasonable way that that balloon looked at 10 seconds, 5 seconds, and 1 second? So you look at these images and you think, right, that's the pattern going forward. If I bring that pattern going backwards, what would that look like instead? And as you can see there, it pretty much looks like the exact same shape. Because reasonably, if it's 20, 30, 40, 50, and nothing's changed to the balloon at any major point, then as you go backwards in time, it should really be the same. It should be the same size for 10, 5, and 1. Okay, so that's going to give us an idea of two ways that we can look at things changing. So what we're going to do is we're going to quickly look at modeling some data to record a changing universe. And we are not going to be reviewing articles, but that's something I would do usually with a different group. So I'm going to take a quick picture here. This is a picture of a nebula. Nebula is a big massive gas cloud that is considered to be the birthplace of stars, or the nurseries of stars. And within nebulas, the gas of hydrogen can condense and grow into a big star, which can form the solar system. So as you can see, looking at this, there's quite a lot of stars kind of being generated in this nebula. So what we're going to do is we're going to pick one of these nebulas. Sorry, what I should explain is this is a photo taken of the nebula, and then 1 second later, the photo was taken again. And as we can see, things look to be a little bit different. Things look to be a little bit more spread out. So it's a different photo with the same camera and the same settings just 1 second later. So what we're going to do is we're going to put the two of them beside each other. And we're just going to kind of have a quick look at distances between different objects in these pictures. Now this is a class activity I would do. So usually when I'm doing this in class, somebody is going to mention the fact that one of the pictures looks a little bit more zoomed in. And it is, but it is a learning activity. So it's just to kind of show what the data looks like in real life. So we're going to pick a star. I'm going to pick this star over, or sorry, this galaxy actually, the spiral galaxy down the left. And I'm going to measure the distance it has to three different celestial bodies. So in the diagram here, 1 second later, I'll be measuring the distance from here to here. I'll measure the distance from here up as far as here, and I'll measure the distance from here up as far as here. In a classroom, I get students to actually do this on the board. Under, safety conditions, under COVID and all. So masks, sanitize down my meter sticks, and they have to wear rubber gloves. That way we can get them to do this as a class activity. So again, if you just transpose those lines directly, you can see that 1 second later, that the distance from here to here is no longer the same distance, even though it's between this galaxy and this red part here. The distance from here to here is no longer the same as the distance from here to here within 1 second. And the distance from this galaxy to this star has increased. The distance from here to here is no longer the same. So what I need to do is I need to just change the lengths of those arrows. And what I do is I would measure the shortest lengths on both first, the medium lengths on both second, and the medium lengths on both third. And what I can notice is that if I measure them, there's a 5 centimeter difference, which in a scale that I would use in class is 5 light years. In the second picture, the distance between them is now 8 light years. The first picture, the distance is 12 centimeters, which again, 12 light years in inverted commas. And now in the second picture, it's 18 centimeters, which is 18 light years. And the third picture, the third length, it's 20 centimeters, and that becomes 29 centimeters, which again, you can convert to light years. So what we can say there is, looking at these pictures, that we have found this point where everything is expanding away from. It seems to be that everything is expanding away from this central galaxy here, which is kind of interesting because, if everything's spreading away from that single point, then it might be reasonable to assume that that single point is actually the center of the universe, which isn't bad for, looking at one photo and guessing it on your first go. So let's go and have a look at the same photos, but we're going to look at it from a different reference point. So we're going to take this star here in the middle, and we are going to start measuring distances away from that one there. So we're going to measure from here down to this star. We're going to measure from here down to this bright star here. We're going to measure from there up to this bright blue star as well. Okay, and if I transpose the arrows directly, they don't match up. So I'll just need to extend them. And again, in a classroom, I get students to measure the short arrows first, then the medium lengths, and then the long lengths. And what we notice is, well, the nearest one was 3 centimeters, and that became 6 centimeters. So again, 3 light years to 6 light years. The second one was 8 centimeters, which became 16 centimeters, which again, 8 to 16 light years. And 15 centimeters to 24 centimeters. And again, you can call that in light years. So what that tells us is that from this picture, everything seems to be expanding away from this point, which is a bit weird because we kind of said that this is acting like it's the center of our universe because everything's expanding away from this point. But now everything's also expanding away from this point in the exact same manner. So maybe we can test that out at a third place and see how that works in a third place. Okay, so I'm going to use this star over here. Again, I'm going to measure against this one over here. I'm going to measure against this blue one down here. And I'm going to measure against this bright blue one over here. So when I do that, I can see that my arrows don't really seem to match up. Especially that one that was definitely pointing in the wrong direction. So if I redo my distances, and by redoing my distances I can then just now start to measure them, I can see that what was 4 centimeters, which is the short distance, became 7. What was 14 became 20. And what was 22 became 31. So this seems to see that that point is the center of the universe as well. So this is the center of the universe, and this is the center of the universe, and this is the center of the universe. That doesn't make sense because you can only have one center. So we've learned that the idea of there being the center of the universe it's a little bit harder to look at than really makes sense. So, a couple of things I want you to think about. If you're standing on one galaxy and you look out at the others, do the other galaxies appear to move towards you, away from you, or do they remain the same place? So, if I pick this place, or this place, or this place, or maybe this one, or this one, or this one, or pick any celestial body there, when you're looking out at everything else, do they look to be moving away from you, moving towards you, or staying still relative to where you are? So that's one thing you need to think about. Second thing is, If you're standing in one galaxy and look out at the furthest galaxies, so the further away you're looking, do they seem to move away faster or slower than the galaxies that are closer to you? So are these galaxies moving away, or appear to be moving away, at the same rate as these ones if you're using this as your reference point? The further you go away, do they seem to move away faster or slower or at the same rate? Okay, so just give yourself a moment to think about them. We'll just discuss the answers now. So, what we can learn from these photos. These photos tell us a few things. One, the universe is continuously expanding. Space itself is what's actually expanding, not the celestial bodies inside them. What that means is the distance between all the parts is getting bigger and smaller, but the actual celestial bodies themselves are fine. All points in the universe expand away from each other. There is actually no point that we can consider the center of our universe. It's odd to think about it, but the whole universe doesn't have a center at all. And finally, the further you move away, the quicker the rate of expansion. This idea here links, if we go back to what our universe looks like. Based on what we look at now, we can see that the universe is expanding as time goes on. So if we reverse time, then it's reasonable to assume that the universe was a single dot in small space, and that occurred 13.7 billion years ago.